Welcome to the next lecture in the course on software design and modelling. So this part is entitled Good Code because although I talked earlier about how the focus of this course is good design, what it is and how we can achieve it, it's worth spending a few minutes thinking at a slightly less ambitious and lower level stage about what it is to be good code, the kinds of things that we can evaluate by looking not at the overall design of an entire system, but at a few hundred lines of software code that might be in front of us at any one time. So here's the plan for this lecture segment. We're going to talk about what it means for code to be good and why it's important, and finish up by emphasizing why good code on its own is not enough to make your software have all the good characteristics that you would like. So I said that you are assumed, if you're taking this course, to be competent at programming in Java. In other words, I'm assuming that you can write code. What I'm less sure about is how much understanding you have of how you can tell when you've written good code. This gets emphasized more or less in different introductory programming courses. It's been on my mind a lot lately because, inspired by the need to have a book that I could recommend to people taking those introductory programming courses, such as the ones that we have in our first year here, I decided to write this book, How to Write Good Programs, specifically in order to address the issue of, well, how do you really write good programs, good code, and how do you learn to do it? You, of course, are way beyond the target audience for this book, so I'm not suggesting that you all rush out and buy it. I'm just trying to explain where I'm coming from in thinking about this. So I've already kind of switched between talking about coding and talking about programming, and this is a course about software engineering. So it's maybe worth putting on the table that these things are related and but slightly different disciplines. So the way I'm going to use the term, we've got increasing levels of responsibility, if you like, going up from there. So I'm going to say any software engineer can program and any programmer can code, but not necessarily the other way round. So the connotations we've got here are that somebody who is just coding, and this is typically the term that gets used in schools, for example, is probably not taking much responsibility for deciding exactly what the program should do. They're probably more or less coding what they're told to. Or making purely personal decisions to please themselves alone. Whereas once you're up at software engineering, you really are talking about somebody who needs to be taking a professional view, balancing different requirements from different points of view, thinking about the long-term life of the software system, and so on and so forth. And programming is kind of in between. So those are the connotations I'm going for anyway. So I'm going to claim that the two major characteristics of good programs are, one, that they do what they're supposed to do, and for short we'll say that they are correct, and two, that they are clearly written. So let's look at those one at a time, and let me try to convince you, if you need convincing, that they are important, and let's think a bit about how we can ensure them. Well, hopefully it's not too difficult to convince you that if the code doesn't do what it's supposed to do, it may be useless, or it may be worse than useless, depending on what it actually does do and how much people need it to do what it's supposed to do. But the $64,000 question is, of course, what does it mean to be correct? Correct with respect to what? So if we have an explicit idea of what the code is supposed to do, then that is usually called a specification. And one kind of specification that we might have is a contract, the term chosen by analogy with legal contracts and sometimes even forming part of a legal contract, and we'll talk about the kinds of contracts that we have for object-oriented software later. But both of those things are potentially rather legalistic. We might ask, well, what about the user's actual needs? Isn't that what we really mean when we talk about code doing what it's supposed to? And this brings us to the distinction, which is a very important one in software engineering, between verification and validation. And the very neat distinction between these two is that if you are interested in verification, you are asking, have we built the software right? Okay, so have we, starting from a given specification, applied sensible techniques to ensure that the software correctly implements the specification we were given? And if we're interested in validation, we are asking, have we built the right software? In other words, never mind what the specification actually says in detail, does this software actually meet somebody's needs? Okay, and you want decent consideration of both of those questions, of course. And the key difficulty, the reason why those two things aren't the same, is that any other artifact, for example a specification or a contract, with respect to which the code is supposed to be correct, may itself be incorrect in an informal and therefore really important sense. And we'll have a lot more to say about this kind of thing as we go. But this is one of the key ideas. Your code should be correct with respect to something or other. Once you've understood what it is to be correct, then in order for your code itself to be correct, it jolly well better be correct with respect to that thing that you decided was right. In other words, it shouldn't have bugs in it. Worth saying a bit here about the extent to which we do or don't focus on code as all there is. Agile, starting with extreme programming and going on into many other approaches to agile software development, came into being as a kind of back to basics movement, as a reaction to approaches to software engineering which had become far too high ceremony, far too document centric, with too much emphasis on written specifications and too little emphasis on high quality code. So it may be the case that today coding is actually a rather small part, often a surprisingly small part, of what a typical software engineer really spends their time doing. But there's an argument that because the code is what the stuff that actually runs in the end, and it's the code that really has to be good, it might even be that software engineers perhaps ought to spend more of their time coding, and you will find people who argue this, and we may even have the argument later on. So we will have more to say about agile development later, but one of the things we might think about is how agile software development handles this issue of correctness. What does it mean to be correct? I said that it's not really very big on documents, so it's probably not by having a 500-page specification. What it is by having tests. So tests themselves can be used as a kind of specification, and the name we used for using tests in that way is test-driven development, and again we'll have more to say about this later on. But the idea here is that you should have tests for all production code. The tests should always be up to date. The tests should be written before the code itself is, and then the tests themselves form the reliable oracle as to what the software is actually supposed to do. The code is then correct if and only if it passes all of the tests. This, however, is actually a part of the agile philosophy that often tends to get left out. You will sadly hear people say, oh, in our company we use an agile approach, and then you'll say, you're using test-driven development then, you have tests for all production code. People will at that point look a bit shifty, and you'll find out that no, they don't actually do that. One of the reasons why it's hard is because requirements change, and then you have to change not only the production code but also the tests, and people can get into a state where they feel that that's rather a lot of effort, and couldn't they just write the code and worry about the tests afterwards in the old-fashioned way. The key challenge, which is what agile software development was invented to handle in the first place, was the attempt to make change cheaper. Okay, so how do we reconcile these things? That the purpose of agile software development is to make change cheaper, which is really essential to delivering all of the software that we would like to have in our societies at an adequately low cost, while at the same time this key technique that's part of agile software development is perceived to be too expensive because changing the tests is too hard. Well, a key element of this is to have clearly written code and to keep your code clearly written. And so that brings us to the second key criterion. I introduced it in that way because of the fact that clearly written code is often seen as, particularly by students I have to say, as being not very important. It's seen as the kind of thing that your university professors care about, but a proper professional wouldn't really be too bothered by. Nothing could be further from the truth. Okay, the interface between the code and humans, the humans who write it and the humans who have to read it and the humans who have to modify it when things change, is just as important as the interface between the code and the computer. Okay? And what we mean by code being clearly written is that it's easy to change it and keep it correct when necessary, because a person who comes along and looks at the code can easily understand what it's doing and can easily understand how to change it in order to meet the changed requirements, whatever they might be. Now, some elements of what it means to be clearly written code are extremely basic, and nonetheless important for that. Okay, so layout, just really stupid stuff like, do you have consistent indentation? When you decide where to put your curly brackets, do you do it the same way on all your functions? Do you manage not to have your lines running together in weird ways? It's absolutely boring, and these days there's really no reason for you to be wasting brain power on it, because your IDE can do that stuff for you really quite effectively. So make sure you know what the keyboard shortcut in whatever IDE you are using to develop your code is for correcting the layout, and use it frequently. Equally boring is that in any programming language that you use, you will find that there are certain conventions about a whole bunch of stuff really, but one of the categories of conventions that you'll come across is conventions about how you should capitalize the names that appear in your program. So for example, in Java we have a very strong convention, which is that your class names always start with a capital letter and your methods never do. But the compiler will not enforce that, and so it's possible to get it wrong, and people do. Okay, but getting those conventions wrong, in other words not following them, is one of the easiest possible ways to completely confuse the reader. Okay, even if they manage to see past what you've done and they say, oh yeah, this lowercase thing called customer isn't an identifier or a method name, it's actually the name of a class, they have to put a certain amount of cognitive effort into overlooking those things, and cognitive effort is in short supply when you're trying to understand complicated software, especially if you didn't write it. And so by obeying those conventions, and that means of course not only obeying the ones you know about, but also paying attention to what other conventions there might be that you haven't noticed yet, you can make the life of anybody who has to read your code later, including you when you're older and wiser and more experienced, easier than it would otherwise be, and it really is worthwhile. So do that thing. Consistency is a broader thing than that, and can apply at the level of particular systems as well as at the level of entire languages. So for example, within a given software system you might have a convention about how errors of certain kinds were handled. So, which exception would you be raising, or are you going to be returning an error code from certain kinds of methods, and where are those exceptions handled, or what is going to be done with the error codes. And the more consistently these things can be done within a given system, the easier it is for somebody to understand what's going to be done when they're trying to understand the code in order to change it, and the more effort they will have to spare for the more specific parts of their task, and the more likely they are to get it right. Beyond that, we get on to some more interesting aspects of what it is to be clearly written, and there's a reading which I will have you use, I think, later on in the course, but as a sort of pre-advertisement, let's say names are really, really important. So picking the right names that adequately describe the thing it's a name for. So if you've got a class, you want to give it a name that reflects the domain concept that that class represents. If you're going to give a method a name, you should give it a name that conveys to the reader what that method is going to do. And this sounds obvious, but it's actually really quite hard. And of course it interacts with change, because what your method does precisely when you write the first version of it might not actually be exactly the same as what the same method does 2 years down the line after it's been modified and maintained in a whole bunch of different ways. And so one of the things that you do in order to keep your code clearly written is to change names from time to time. That brings us to refactoring, which we'll talk about later on. And one of the things that's very interesting is that it turns out that a clear choice of names and a clear, easy to understand structure for the program are very synergistic, and it's interestingly possible to drive the process of improving the structure of your software system through consideration of whether the names are as clear and appropriate as they could possibly be, and through the process of fixing them so that they are. And you'll see some examples of that later on. So you can improve code a lot just by looking at what's in front of you and optimizing that. But sometimes you do need a more bird's eye view. So if, for example, you decide that your class is not ideally named at the moment, one of the things you have to consider is not only what do you see inside the class when you look at the implementing code of it, but also what does it mean to its clients? What purpose is it serving to the clients? So what do they need to, what's an appropriate abstraction of what this class is? What's a good label for what it does from the client's point of view? And so this takes us to a more sort of high level, less local perspective of what it is for code to be good. Sometimes you can have some kind of high level convention, and frameworks may help you, but sometimes you have it that in order to pick the best names and to understand what's going on and how to restructure your code at a high level, you are going to turn out to need a way to get a high level structure into a human's head, and that is where we start to need modelling. That's a good place to stop.